via gravitational lensing. But both the baryonic matter and the dark matter will have an effect, a gravitational effect. So we can use our observations, which usually look like this, 4 points of light, because the quasars we select have 4 lens images of them. And we will use the reflections and magnifications to analyze both the structure of the lens galaxy in the baryonic and dark matter component mainly, and also the properties of the quasar itself. So gravitational lensing. As we all know, mass, accumulation of mass and energy curves space-time, and the light which travels in geodesics to the 4-dimensional space-time is deflected in the 3-dimensional space. So if we have a source far away and a lens, a gravitational lens in between, we can see, instead of just one image of the source, some light that will not reach us in the beginning will be deflected towards us, so we see multiple images of our faraway source. Now, usually in our systems, the source is thousands of megaparsecs away from the lens, and the lens is also really far from the observer, so what we use is the small lens approximation, so we can do geometrical optics, as long as we use the angular diameter distances in cosmology, because they compensate for the expansion of the universe and the weird things that happen. I won't enter that. But the important thing to remember is the deflection angle that a light ray suffers depends. Here, the case here is a circularly symmetric lens. It depends on the enclosed mass within the impact parameter, the distance from the center of the lens where the ray travels through. Depends on the mass and is inversely proportional to the impact parameter itself. Now we have a household object which deflects light in a similar way. The closer it gets to the center, the more it gets deflected, which will help us visualize what's going on in our systems. The object is a wine glass, and here, just with the computer charger acting as a source of light, if we put one in between, we can go the distortion that the lens creates. We need to do the derivative of the deflection angle, which means the second derivative of the potential. And this matrix is the inverse of the magnification matrix, and it's called that because the determinant gives us the magnification that an element of the source plane will have. But the important thing to remember is the magnifications of the images of the quasar depend on the second derivative of the potential, which means they are more sensitive to possible substructure in the lens. Now, why do we use quasars as sources? Well, this is a quasar, one of the first discovered, and they are very bright, faraway point sources. So we can study the fluctuations of the images instead of having an extended object that's hard to see. The name comes from quasi-stellar radio sources because they are very point-like and they were discovered in radio at first. When spectra could be taken of them, we saw that they had a large redshift, which means they were very far away, so they had to have a very high luminosity, higher luminosity than the brightest galaxy known at the time. They are also compact and variable, they are very small, and the only possible mechanism to produce such amount of energy in less than a cubic parsec is accretion of matter into a supermassive black hole, converting gravitational energy into kinetic and radiation and everything. This is a representation of the accretion disk itself, which emits light in a continuum, and it goes from X-rays in the center and even in gamma rays in some cases all the way to the infrared. This is what powers the whole system, light coming from the accretion disk. It has a peak in the optical ultraviolet, and the size is compared to the rest of the quasar is small, a few light days across. Now, these clouds that I try to draw here is the broad line region. There are clouds of gas that, due to the high speeds, are seen in the spectrum as broad emission lines, but they are spread on an area of tens of light years. They are bigger than the accretion disk. While in some systems, these broad lines are not seen, and we believe this is due to a huge torus-like structure of dust that is optically thick, so it doesn't let us see the inner region if the orientation is such as to occult it. This acid torus is warm dust, so it makes thermal infrared emission. The size is much larger, from 0.1 to 10 parsecs, with an inner edge defined by the distance at which the temperature is so high that the dust grains so remain, and it's not very thick anymore. Now, here we have what's called a narrow-line region, which is just ionized gas and mechanical outflow, also powered by the radiation from the vision disk, and it's narrow lines of the center, and this is what caused the radio emission that was detected in their discovery. Their size is at the tens of kiloparsecs or more, so many times they are bigger than the whole galaxy or the quasar. But the important thing is, we have several components of different sizes emitting at different wavelengths. So we use observations for all of these different wavelengths of light to study the invisible, dark matter. Well, what's dark matter? It was first proposed in 1930 by Zwicky because the galaxy clusters, the galaxies in them were moving too fast to be bound gravitationally by the luminous matter that we could see in them. So it was proposed that perhaps some kind of extra invisible matter was there. In the 1970s, Vera Rubin also showed that we need a spherical halo in galaxies instead of just a disk to explain the rotation curves. Since then, many other lines of evidence have substantiated this claim, and now we know that we have to include about 85% of matter in the universe, which does not interact electromagnetically to reproduce the observations. As far as we know, it interacts via gravity. So, gravitational lensing is a very good tool to show its distribution. And also, we know that the components, whatever makes up dark matter, it travels at non-relativistic speeds, because otherwise the universe would coalesce in a different way. So the leading model that explains our observations is the cold dark matter model. Problem: when we do simulations of cold dark matter to reproduce our own Milky Way, or galaxies like our own Milky Way, we get a halo of dark matter like this. Instead of a smooth halo, we see that about 10% of the subhalos that coalesce to form this halo, about 10% survive the tidal effects to our days. There's about 1% in the central regions, which accounts for thousands of satellites that we don't see as luminous satellites in galaxies like ours. So this problem has been called the missing satellites problem. And there are two solutions to this. Either they do not exist and we have to modify the models or the simulations to account for them for the absence in some way, or they do exist, but devoid of stars. Perhaps they were devoid of gas in the early stages, or there was no star formation in them. But anyway, the fluctuations in quasar lensing would be sensitive to their presence. So we can use our observations to probe, to see if one of these is right. Now, onto the first part of the actual research bit. We will determine the structure characterization using methods. The system we observe is the Einstein cross of QT2237 plus 0.05 for astronomers. And why is this system important? Well, first, it's the closest lens galaxy known, with the lens galaxies relatively nearby compared to the quasars, especially, and other lenses. This causes the quasar images to go through the bulge of the spiral galaxy instead of 1, 0, 0, 0. This and the high relative speed between the lens and the quasar, because the lens is very close, causes noticeable additional gravitational lensing effect caused by the stars of the bulge. This it will also split the images of the quasar, but the splitting will take place in a scale of microseconds, so we don't have enough resolution to see it. We only see changes in the brightness of the images. So we call this the effect microlensing using medium infrared fluxes from the source, from the researcher, and the microlensing, which is calculated with magnification maps, which is what we saw before with acoustics, one for each quasar image. We compose these maps with a disk brightness profile at each wavelength to see the microlensing effect smoothed out. And then we choose a random location at each map, calculate the flux ratios between them, and compare them with the observations using this chi-square function. Which is just, these are two different images, so we have a flux ratio between one image and the other, minus the magnification, and the macro lensing magnification between the two images, and the flux ratios of the positions in these two maps. We do it with all 6 possible pairs, and to account for the 5 wavelengths, we sum the results in each case. Now, we repeat this process 10 to the 8 times to sample the magnification maps properly, and the probability of reproducing the observations with these two parameters is this sum. So the larger this difference, the lower the probability of reproduction. Consistent with each other, consistent with the previous results from other groups. Now, perhaps this variability in the Prism disk is due to microlensing, and this assumption we were using was wrong. So either if there are systematics changing the values or microlensing, we can use them to estimate the size of the near-infrared emitting region, as we did before, and see what happens. So we used a Gaussian brightness profile this time, because it should not depend on the profile as we showed before. And we get a half-life radius for the total for the near-infrared emission region of about 200 light days. But there's a problem. The luminosity of the quasar is quite high, and the minimum radius for sublimation of the dust is it's about 1500 light days. So this should not be possible. So we have two possibilities here. Maybe there's extra emission from a small source. Maybe the external regions of the Prism disk have a mid-infrared component that has to be accounted for because it would be microlens. It would produce brightness changes in the flux ratios in mid-infrared. Or this variation is due to the systematics. So we take this value as a lower limit for the mid-infrared emission. So what we can say for sure is that we measure the mid-infrared emission region of this quasar using microlensing at larger than 200 light days. Okay, with the radius larger than 200 light days. Now to the dark matter structure. We're going to use mirror lensing, which is there's no microlensing because it's a bit stronger effect, to estimate the mass and abundance of a distribution of dark matter subhalos in the halo of the length galaxy. We want to reproduce the mid-infrared observed fluxes. We will use the weighted average because it should be less affected by microlensing. And using a kind of a microlensing method similar to the previous one, but will be explained in the further section. Using the difference to calculate the flux anomaly, we take the true flux ratios, the ones predicted, like the flux ratios of the smooth distribution as the ones predicted by the central anomalies due to the substructure. We need about 3% of the mass surface density in the central regions of the galaxy in subhalos to reproduce the flux ratios that were so hard to reproduce with the smooth model. We cannot constrain the mass of the subhalos, however. If we use a more detailed model, then I'm not going to why as well clear, we only need about 1.3% in subhalos to reproduce our flux ratios. So the cold dark prediction in the central regions of the halos is about 1%. And we have real difficulties to use a smooth model to reproduce these flux ratios just by modeling without substructure. So maybe this is an actual estimation of the substructure in this system. It is consistent with the prediction. So then we see a flux anomaly there. Could be due to structure or microlensing. Well, our flux ratios when observing in the X band, which is are 1.98, 1.98. So it's very close to the prediction. We don't see this normally. Now, when trying to feed the model to a point source, we get some residuals. So perhaps it looks like the source is extended. It's not very punctual. It's not a point source. So we can use this to try to estimate the size of the source itself. So when the model was fit with an elliptical Gaussian, we reproduce the image much better. Residuals are lower, and we can estimate the source size of about 70%. Now, this system was also observed by other people with the E-Merlin interferometer, which is formed by many old radio telescopes in the United Kingdom. So it has a baseline of about 200, a maximum baseline of 200 kilometers, a shorter wavelength. So we can study the spectral index of the quasar, which is minus 0.55. It's steep instead of flat. Now, this system is also very interesting in lensing because it has flux anomalies in the optical and also in infrared. In this case, it's near infrared. And we also have C-band. We also observe flux anomalies, but they are not the same as the infrared ones. In some ratios, they go the opposite way. And some ratios are some brightness. The indexes. Restart. The brightness of some of the images is larger, is higher than the infrared ones, and some of them is lower. So what's going on here? Well, if we try to fit a point source to reproduce the flux ratios, the model has to be, it's not an isothermal ellipsoid like we were using before. We let the density profile to vary, and we need a very steep density profile and bigger predictions of this manipulation match with the observations, and obtain the Bayesian probability of better parameters to reproduce the actual observations. Problem: we cannot use here a single magnification map for all cases, or a single size of the magnification map for all possible cases, because sometimes the subhalos are too big, so we just get part of the central acoustic of one subhalo, and we can sample the probabilities well enough. Or maybe there are not enough subhalos, perhaps there's one subhalo here, one subhalo there, or no subhalos in this region, so we don't see any acoustics. Or too many subhalos in the cases with lower masses, so it becomes impractical to calculate the deviation, the deflection of each single subhalo in each light ray. So what we have to do is many maps for each pair of parameters to achieve good statistics, vary the sizes in case we need to do smaller maps to account for the many halo spaces. And we calculate the probability distribution function of magnification from the whole map. So we sum all the pixels with an anomaly caused by subhalos of between this value and this value, and we do that with from minus 5 magnitudes plus 5 magnitudes in beams of 0.05 magnitudes. So here's a sample of the magnification maps. Each of these clusters is caused by a halo, but they are very sparse. So we cannot really use the random positions and sample the whole map or the whole amount of many maps without the need of a huge amount of random positions, because we need too many. So this is what the probability distribution function of magnifications from one map usually looks like. Most of the pixels are not magnified or demagnified, and some of the pixels have flux anomalies caused by this behavior. What we do is we have a measured flux anomaly between the two images. So if we have this flux anomaly, if for each pixel of one map that is demagnified to reproduce, then perhaps the anomaly, if it goes in the other sense, In the other way, we reproduce the actual flux ratio observed. So anyway, what we do is we displace the probability distribution function of the modifications from the whole map by the observed flux anomalies. So we have, these are our flux anomalies predicted, these are the observed ones, and when multiplying them, we'll have the probability of the distribution of subhalos of reproducing the flux ratios we observe in the system. We do this with the 4 Quasar images in our systems, and then we multiply 4 of them and integrate to obtain the probability of that distribution. We have preliminary results, and the exponent of 1, 5.3, which is steeper but marginally consistent than the thing in this prediction. It has to be said that we measure an object of about 8 light days, but it's about 10 billion light days away from us. So the microlensing method is very powerful to do things that if they are completely impossible otherwise without lensing. Then we use mid-infrared observations with GTC. We calculate the results. We get a consistent result with this. I will also go further by estimating a size for the mid-infrared emission region, which take more than 200 light days, and a fraction of mass in subhalos of about 1-3%. Then we detect 4 radio-quiet quasars in radio. We find no evidence of such structure, and radio emission is likely due to the active-reactive nuclear mechanism. And finally, we develop a method to estimate the abundance and mass of dark matter subhalos by scanning mirror lensing a sample of these quasars that already have mid-infrared, radio, and nanospectral light observations. And our preliminary results are an average mass of the subhalos of about 10 to the 6 solar masses, and abundance of about